So we're going to take what we've learned from our vectors and our parameterization of curves and apply this to motion in space. So for this section, or at least the beginning, we're going to let our parameterization R of t, we're going to use this to describe the motion of an object. So this would be the position of an object at time t. And taking that into account, then r prime of t, which we'll denote as v of t, is the velocity. And the second derivative, which is also just the derivative of the velocity, which is a of t, is the acceleration. And we'll use this, we'll be able to recover a lot of the elementary motion arguments from physics class using just this and what we've done with Calc 3. So let's just recall a couple of things here. In general, the force is given by the mass times the acceleration. And then if we're looking at the force of gravity on Earth, we're going to take the magnitude of this as 9.8 meters per second squared. So those are a couple of things from physics that we'll want to remember. And now we're going to go ahead and see how all of the equations that we use for motion in physics come about. And we're not going to assume we know anything more than the stuff we just covered about what's going on. So let's start with an example. Maybe thrown really hard or shot out of something at an angle of 27 degrees to the ground. Okay, so let's say if it lands 120 meters away, so it travels it lands 120 meters from where we're standing, what was the initial velocity and speed? So this is the type of problem you would encounter in a first course in physics. Let's go ahead and see what we've got going on here. So we know the only acceleration we're going to consider here is going to be the acceleration due to gravity. So let's start with taking a of t to be minus 9.8, and we're going to take it in the j direction. So we're setting up our coordinate system like this with x and y here. And so the gravity is pointing downward. So we can think of the ball is going to go up and gravity is going to pull it back down. We know this initial launch angle is 27 degrees, and this distance is 120 meters here. So then to get the velocity, we know we integrate the acceleration. So this is going to be minus 9.8 tj plus our initial velocity. And notice our initial velocity here has to be a vector. It's not just a number. And then our position function is going to be the integral of the velocity function. And so this is minus 4.9 t squared j plus the vector v0 times t plus some constant, which we'll say is the initial position. So let's let v0 be the magnitude of the initial velocity. So this is also the initial speed. And let's think about what we have here. So our initial velocity is looking like this. And we have this is 27 degrees. So if we want to break the velocity up into its components, this is going to be the magnitude of v0 cosine of 27 degrees I plus magnitude of v0 sine of 27 degrees j, or if we want to use the notation for the speed, so that gives us our initial velocity. And then we know our initial position, the way we chose our coordinate system up here, was equal to 0. So our initial position is just the 0 vector. So now we have everything we need now. So our velocity, we can combine these things. So I have the I component is v0 cosine of 27 degrees I, and then the j component is v0 sine of 27 degrees minus, and we had that 9.8 t. And our position is going to be given by, well, we didn't add anything to it, so it's just this initial velocity. So I'm going to have v0 cosine of 27 degrees, and now I have a t with it, plus t v0 sine of 27 degrees minus 4.9 t squared j. So that gives us everything we need in order to figure everything out now. So let's figure out, when does it land? Well, we know it lands when it's moved 120 meters in the x direction, and when the y value, or the j component there, is 0. So this is going to be, we know v0 cosine 27, and let's put the t out front, and let's call it t0 for the landing time. This is 120 because that's the x component, and we also know the y component should be 0. So we can combine these things. So this first one is going to give me that t0 is equal to 120 over v0 cosine of 27 degrees. And then this bottom one I can factor out. I can say t0 v0 sine of 27 degrees minus 4.9 t0 is equal to 0. And so this leads to two solutions. t0 is equal to 0, so that's going to be corresponding to when it was launched. And then this solution is going to be corresponding to when it lands. So this one is the one we're interested in, and this leads to t0 is v0 sine of 27 degrees over 4.9. And so now we have two equations here. I have this and this equation, so let's set those equal to each other. So I have 120 cosine of 27 degrees, or sorry, that goes in the denominator, so over v0 cosine of 27 degrees is equal to v0 sine of 27 degrees over 4.9. Now remember, we're interested in the speed and the velocity, so we want v0. So let's multiply both sides by v0, and I'm going to get v0 sine of 27 degrees, square on the v0, over 4.9 is 120 over cosine of 27 degrees. So v0 is the square root of 120 times 4.9 over sine of 27 degrees cosine of 27 degrees. And this is approximately 1453.6 meters per second. And so that gives me my speed when it lands. or my speed when it launches, not when it lands. This is the initial speed. And then my initial velocity, we just plug that in. Remember, when we look up here at our initial velocity, we just have the magnitude times the cosine 27 and sine 27. So then this initial velocity is going to be approximately 1453.6 times cosine of 27 degrees I plus 1453.6 sine of 27 degrees J. And this is why I said shot from the ground and not thrown, because this is going pretty fast. Okay, so if you've taken physics, you've probably seen an example like that. Let's look at another example, but now let's take into account of being in three-dimensional space instead of just this two-dimensional space. So let's say a ball of mass 2 kilograms is thrown in the air with an initial speed of 20 meters per second. And it's in the northwest direction. At an angle of 30 degrees with respect to the ground. So let's say a wind applies a force of 5 newtons in the southwest direction. Okay, where does the ball we want to know, where does it land and what is its speed? On impact. Okay, so let's think about what's going on with our acceleration here. So let's start with our acceleration. Remember, our force is mass times acceleration. So if I want the acceleration due to the wind, well, let's think about our coordinate system here. So we're going to set this up as x and y first, and the wind is only applying in the southwest direction, so we can ignore the z variable right now for this part. And so it's going southwest, so it's going in this direction here. And we know the magnitude of it is 5. And so the acceleration is 1 over m times the force due to the wind. And now we want to break this up into our components. So if we think about what this vector here is, there's a 5 for the length, and then we want the unit vector here. So this is minus cosine of pi over 4I minus sine of pi over 4j. So this is 5 root 2 over 4, and then I have I plus j. And now we're taking the x and y plane here to be the ground, and so the vertical axis is going to be our axis with respect to up and down. So our acceleration due to gravity is going to be in the negative k direction, so minus 9.8 k. And this is usually where it gets a little tricky, because everybody's so used to using just the x and y axis, it's easy to think that the vertical direction should be j, but in this case it's k. So our total acceleration then is the acceleration due to the wind plus the acceleration due to the gravity. And so this is minus 5 root 2 over 4I minus 5 root 2 over 4j minus 9.8k. So that gives us our first vector that we need. So now we want to look at the velocity here. So we know that the velocity, just like in the previous, is the integral of the acceleration. So this is going to give me a minus 5 root 2 over 4 ti minus 5 root 2 over 4 tj minus 9.8 tk. Then I also have to take into account that initial velocity. And the initial velocity is where things are going to get a little bit tricky here, because now we need to work in 3 dimensions. So let's see, do our best to draw this. I have x, y, and z. And let's draw our initial velocity here. So it's going something like this, where this angle is 30 degrees. This vector is our initial velocity. And then we know, we were told it was going in the, oh, it said northwest direction. So I messed up on this. So we need to change the labels on these. So let's go ahead and change our axes here. So northwest means this should be my y and this should be my x, like this. And then we know that this angle here, since it's northwest, this is 45 degrees. So my velocity, initial velocity, well, the easiest component, so let's leave it, who knows right now for these two, but the z component is this part here. And since my initial velocity was 20, we know the magnitude of v0 is 20. So this k component is going to be 20 sine of 30 degrees, k. And now for the other components, notice what we're getting here is, let's draw this in the xy plane. So in this case, if we project this down, it's going in this direction. And we know this is 45 degrees, this angle here. And this length here is the part that's sitting in the plane. So this is going to be 20 cosine of 30 degrees. So that means when I write out what this triangle here is, this vector here, let's call this W for, oh, let's not use W for wind. Let's call this U for a second. So U is the vector, well, the hypotenuse is 20 cosine of 30 degrees, and then we need the unit vector that's in that direction, so that's going to be minus cosine of pi over 4i plus sine of pi over 4j. And so cosine of 30 degrees is square root of 3 over 2, so this is, and then this is minus root 2 over 2i plus root 2 over 2j. So this becomes 5 root 6 negative I plus 5 root 6 j. And now we can plug that back in for our initial velocity, and we get minus 5 root 6 I plus 5 root 6 j. And then remember, we found our k value was 20 sine of 30, and sine of 30 is 1/2. So this is plus 10k, and that gives us our initial velocity. So now that we know our initial velocity, we can write down our overall velocity. So v of t then is minus 5 root 2 over 4t minus 5 root 6 I plus minus 5 root 2 over 4t plus 5 root 6 j plus 10 minus 9.8 t k. So now our next step is to find the position. So again, we integrate with respect to t here. So this is the integral of v of t dt. And so this is minus 5 root 2 over 8 t squared minus 5 root 6 t I plus minus 5 root 2 over 8 t squared plus 5 root 6 t j plus 10t minus 4.9 t squared k plus our initial position. But we chose our initial position to be the origin by the way we set everything up. So r0 is just the 0 vector. So that means our position vector is just minus 5 root 2 over 8 t squared minus 5 root 6 ti plus minus 5 root 2 over 8 t squared plus 5 root 6 tj plus 10t minus 4.9 t squared k. And now our original problem was to figure out where it landed in the speed. So this lands when the k component is equal to 0. So that means when 10t minus 4.9 t squared is equal to 0. And so this happens when t is equal to 0. We'll factor this side here. You get a t, and then you get 10 minus 4.9 t equals 0. So that happens when t is equal to 0, or when t is equal to 10 divided by 4.9. The t equals 0 is when it launches. So this is the second one is the one we want. And that's after about 2.40 seconds. So then we can just plug these in to figure out the other results. So the speed on impact, this is the magnitude of the velocity at this time. And if you just check that, calculate the magnitude of that vector, that's about 20.63 meters per second. And where it lands, well, that's going to be at our position function at 2.04 seconds. And we can check this is approximately minus 15.85 I plus 8.64 J minus 9.99 K. Okay, let's try another example, a little bit of a different kind of example for this one. Let's say we have water traveling along Okay, so we have that water traveling along a straight portion of a river normally travels its fastest in the center of the river and slows to almost zero movement along the banks. So let's consider a river with banks 40 meters apart. The max water speed is 3 meters per second, and x units from the west bank of the river. The speed is, we'll just say f of x here. This is giving me my speed is 3 over 440 minus x times x. So we can see at the west bank, when we're 0 units away, this is 0. And when we're 40 units on the east bank, this is also 0. Now, what do we want to do with this information? Let's say a boat proceeds at constant speed, 5 meters per second, from, let's say, point A on the west bank to point B on the east bank, directly opposite. So where will the boat end up? So that's the first question we're going to ask. And the second question will be is what if we wanted to actually land at B? Where would we go? So let's maybe draw a quick picture here. So here's my river. Let's say it's flowing like this. And so if I start here at A and I just go straight over, so let's get these going. So my river's flowing like this and B straight across. If I just start my boat going straight across, it's going to gradually move over here like this. And I'm going to end up somewhere here. So that's what we're asking for the first question, is where will we end up? And the second question is going to be, if we want to land at point B, what angle should we start with? Right, so if we have this situation again, if we're at A, since the river is going to pull us, we want to launch something like this, at some angle theta here, and then the river will push us and we'll end up back here at B. So those are our two problems we want to look at. So let's think about what's going on here. So we need to start with our velocity and our speed. So we know that the river is only flowing north. So that doesn't contribute to the east-west speed at all. So our velocity in the east-west direction will just be 5. So our velocity is 5 in the I direction. Now in terms of the J component, we're given this speed in terms of the water, in terms of our distance from the west bank. So at time t, we are 5t units, or I guess meters, did we say? It's 5t meters from the west bank. So at time t, the river speed will be f of 5t, which is 3t over 80 times 40 minus 5t. So just plugging that into our equation. So then our velocity overall is we have to combine these two. So I've got the boat speed for my first component, and then for the river speed, if we simplify this, this becomes 3/2 t minus 3/16 t squared. So that's completely in the j direction. And now if we use that the r of t is the integral of v of t, my position is 5ti plus 3/4 t squared minus 1/16 t cubed j plus r of 0. And we choose our coordinate system, so r0 is 0. So my position is just 5ti plus 3/4 t squared minus 1/16 t cubed j. And we know that this is going to reach, we reach the east bank when 5t is equal to 40. So we've made it all 40 units or all 40 meters in the I direction. So this is when t is equal to 8. So we can plug that into the second one and we get r of 8 is, well, the 40i, because that's what we just figured out, and then we get 16j. So we're actually going to go 16 meters upriver. So when we drew that picture before, when we start off, this is going to pull us up here. So this is a 16 meters here. So now let's try to do part B. So in this case, we're going to start off and we're going to go in this direction with a theta here. And this is still our A, and this is still our B. And now we need to end up at B. So in this case, the velocity of the boat now is not just 5i, because we're going in this direction here. So when I think of this like this, we know the magnitude of this is 5. So in the I direction, we're going to have a 5 sine theta I, and then minus 5, or we can just, we're going to go negative in this direction because we're going down, so cosine theta j. So now at time t, we don't have 5t anymore because we're only going in that direction by part of it. So this is going to be, we're going to have gone, x will now be 5 sine theta t in that direction. So if we put this in terms of our velocity now, we have that this is going to be 5 sine theta I plus minus 5 cosine theta, and then I fill in that formula for the river, and this becomes 5t sine theta, and then 40 minus 5t sine theta, and all of this is in the j. So if we simplify this a bit, this is 5 sine theta I plus, and I'm going to have the minus 5 cosine theta, and I'm going to have 3/2 t sine theta minus 3/16 t squared sine squared theta j. And now we integrate this with respect to t, and again, our initial position is going to be 0, so we can just forget the r0. So this is going to be 5t sine theta I plus minus 5t cosine theta plus 3/4 t squared sine theta minus 1/16 t cubed sine squared. Oops, these should be cosines. Sorry, this is going to make a mess here. Oh. Wait, no, that's correct. Those should be sines. This was correct. Yeah, those are correct because we were plugging in the x here. So that's correct. So this is our equation then. And now we reach the other side. When 5t sine theta is equal to 40. So that's when t is equal to 8 over sine theta. And now we want to force our j component of r of t to be 0, because we want to land at exactly b, so we don't want to have gone anything up the river. So we want to solve, we want minus 5t cosine theta plus 3/4 t squared sine theta minus 1/16 t cubed sine squared theta to be equal to 0. We can factor a t out of that, and so I'm going to have, let's factor a 16t out. So I will have t cubed, or t squared sine squared theta, and then plus 12t sine theta. That should be negative. We factored out let's factor out a negative 16t, and then plus 5 times 16, so 80 cosine of theta equals 0. So we want this equation here, but we already know what our t is. It's 8 sine theta, so I have 64 over sine squared theta times sine squared theta minus 12, 8 over sine theta plus 80 cosine theta equals 0. So these cancel here, and I get 64 minus 12 plus 80 cosine theta equals 0. So I get a 52 plus 80 cosine theta is equal to 0. So cosine of theta equals 80 over 52, which is definitely not correct. So, sorry, this is not 50. 80 over 52 can't possibly be it, because it'd be bigger than 1. So this is 52 over 80. And so then you just solve this for arc cosine of 52 over 80. And you can use your calculator to figure out an approximate value for that angle. So a couple other things. So that gives us a few examples of how this stuff can be used for motion. And so we'll go ahead and stop there with this lecture.